Hi students, now we have to derive an expression for the speed of sound waves in air. We have studied the sound travels in the form of longitudinal waves in the form of compressions and rarefactions. Here Isaac Newton derives the relation for the velocity of sound through air or gases. So first we will be deriving Newton's formula. And finally, we are going to show that Newton's formula is having some discrepancies, some error will be there. So, according to Isaac Newton, sound waves travel in air or gases in the form of compressions and rarefactions. So, the regions where the air molecules are very close to each other, they are called as compressions. And where the air molecules relax away from each other, these are called as rarefactions. C are the compressions, R are called as rarefactions. Naturally, one must know that when air molecules are tightly compressed, heat will be produced. So in the regions of compression, you can see here the air molecules are coming very close to each other. So the pressure increases and the volume decreases, and also due to the compression the temperature must increase. That is the actual fact. So Isaac Newton also assumed that when the air molecules are compressed, heat will be produced. So compressions are those regions where pressure increases, volume decreases and temperature increases. Similarly, the rarefactions are those regions whose volume increases, pressure decreases and the temperature also decreases. Now Isaac Newton assumed that if the regions called compressions have a slightly greater temperature than the rarefactions, there will be a heat flow from the compressions to the rarefactions for a very small time only. For a very small time, there will be a flow of heat from the compressions, from the compressions into the rarefactions like this. Why? Because Newton assumed that the sound travels through air under isothermal conditions. Under isothermal condition, the temperature of the medium should remain constant. So naturally, when heat is produced in the regions of compression, it has a tendency to flow from the higher temperature to the lower temperature. So he assumed himself by mistake there is a heat flow from the compressions to the rarefactions for a small time t. Why? To make the temperature of the medium as constant. Understand that? So according to Isaac Newton, sound travels through air. Sound travels through air under what conditions? Means under isothermal condition. Under isothermal condition. That means the temperature remains constant. So temperature T is equal to constant. But pressure volume changes will take place, because I told you in the region of compressions what the volume decreases and the pressure increases. And in the region of rarefactions the volume increases and the pressure decreases. So what is the equation of state? We have already used for isothermal process. For isothermal process, P into V is equal to a constant. Pressure into volume, this product will be a constant. I am going to differentiate this equation 1 on both sides. So both P and V are variables, means in mathematics you must have studied UV rule, is it not? When you differentiate two variables keeping U as constant, the V is varied, plus V is kept constant and U is varied. So that is called as UV method. So I will keep temporarily pressure as constant and volume is varied, plus volume is kept as constant and pressure is varied. So right hand side is the differentiation of a constant is equal to 0. So P into dV is equal to minus of V into dP. So right side is 0. I take this term V dP on the right hand side. It becomes minus. Or what is pressure P is now equal to minus V into dP divided by dV. Okay? Or once again, or I can also write pressure P is equal to minus of dP divided by dV by V. Okay? dV by V. So this is dP divided by dV. This V is brought to the denominator so that it becomes minus dP divided by dV by V. Okay, now the numerator is dP. Is it not that? That is what the pressure. So pressure is not, that is also what the dimensions of pressure only. Change in pressure. That is nothing but force per unit area, and that is equal to stress. Whereas this dV by V is a change in volume by original volume, so that it is volume strain. Understand? So this is a bulk stress divided by volume strain, so that this pressure is nothing but this is equal to bulk modulus of elasticity at a constant temperature T. Okay, therefore P is also equal to the modulus of elasticity Bt. Why this minus sign? Whenever the pressure increases, volume decreases. Whenever the pressure decreases, volume increases. The reverse. Therefore, there is a minus sign. So P is equal to Bt. Understand that? Okay. Now, what is the general expression for the velocity of a longitudinal wave through any gas? The velocity of longitudinal waves. Here, velocity of sound waves I will take. So, velocity of sound waves or any longitudinal wave V is equal to square root of the elastic constant. Okay, the elastic constant divided by density. This is the general expression we have studied earlier, is it not? So in this expression, in place of the elastic constant, bulk modulus of elasticity at a constant temperature. So I can also call this Bt. Okay, so this is Bt is isothermal elastic constant, isothermal bulk modulus, okay, of elasticity, isothermal bulk modulus of elasticity. So in place of Bt, I can substitute the pressure of the gas P. Okay, therefore now V is equal to square root of P divided by rho. Okay, so this is one of the important derivations. So velocity of sound in gases or in air is equal to square root of P by rho, where P is what? The pressure of the gas. Suppose you take at NTP, normal temperature and pressure. Okay. So the pressure of the gas is given by the expression H rho G, where this rho is the density of mercury in the barometer. Understand? In this expression, rho means what? This is the rho for the gas. This is density of the gas. This is density of the gas through which the sound travels. Whereas here, this is density of mercury in the barometer. Okay. So this pressure P is equal to H rho G. Normally, if a barometer is kept in this room, means the mercury inside the vertical tube of the barometer will rise up to a certain height. At normal temperature and pressure, to how much height the mercury will rise? It is 76 centimeter of mercury. Understand? So this is 76 centimeter. 76 centimeter is what? H is equal to 76 into 10 power minus 2 meter. And rho for mercury. So this is for mercury, Hg. And this is equal to 13.6 times. It is denser than water. So this is 13.6 into 10 power 3 kilogram per meter cube. And G is the acceleration due to gravity, 9.8 meters per second square. Okay. Therefore, density of the gas. Okay. Density of the gas here is what? Air. So this is equal to 1.293 kilogram per meter cube. This is the density of the air through which the sound is traveling. So I am going to substitute. All these values. Okay. In this expression. Okay. In this expression. Therefore, velocity is equal to what? Velocity is equal to all these values I am going to substitute. So this is 76 into 10 power minus 2 is becoming 0.76 into 13.6 into 10 power 3. So this is 13.6 into 10 power 3 into 9.8. So this is in the numerator. Suppose you substitute all these values and divide by 1.293 means it is found that it is nearly equal to 280 meters per second. If you substitute and calculate the value, it is very nearly equal to 280 meter per second. So, according to Isaac Newton, the sound travels at a normal temperature and pressure through the air with this velocity. But experimentally determined velocity, what V experimental is equal to 332 meters per second. This is the experimentally determined value. How much it is differing, you see, 280 is differing from 332 by large value. So, the percentage error, if you calculate, the percentage error in the calculation of velocity is equal to what? 332 minus 280 divided by 332 into 100. Percentage. This is coming nearly as 16%. 15.67 like that percentage will come. We have rounded that off to 16%. It is a very large error, is it not? 16% error is coming. That means there is some mistake in his calculation. Okay. So, this Newton's formula is not accepted. It is having some discrepancies. So, according to Isaac Newton, sound travels through air and gases under what condition? Isothermal condition, by keeping the temperature as constant. So here only in the assumption there is some mistake. This mistake was realized by another scientist, namely Laplace, and Laplace has corrected Newton's formula by assuming that the sound is not traveling under isothermal conditions, but it is traveling under adiabatic conditions. That is the next topic I am going to derive. I hope you must have understood Newton's formula. Fine.